Hello everybody, my name is Sabornawaj Berry, and today we'll be talking about coupled oscillators. Oh, and I'd like to thank the open source notes provided by Harvard on coupled oscillators. They were really helpful and they were the main source for my understanding. We've talked about simple harmonic motion before. So, for example, an object like this, we offset it a little bit. Oh, sorry. So for an object like this, we can make it, sorry, can you cut? So for an object like this, we can offset it a little, like that, away from its equilibrium position. We can squeeze it, or we can stretch it.
What is the x and y axis?
What? This isn't a graph. So we can squeeze it, or we can stretch it, and eventually it will oscillate. And if it's damped, then it will oscillate less and less before coming to rest around its original equilibrium position. So we've explored both of these scenarios before. But today, we're going to explore something quite different. So, as you probably know, a couple means two. So, naturally, coupled oscillators mean two oscillating bodies. So, let's draw the simplest case for two oscillating bodies. So, we have B1 over here, and actually I'll draw that a little bit bigger. So we have B1 over here and B2 over here. And to simplify things, we're going to let both of their masses be m. So then we're going to have spring 1 with spring constant k, spring 2 with spring constant k prime, and spring 3 with spring constant also k. And we're going to call these spring 1, spring 2, and spring 3. So, essentially, here's what we're going to do. We're going to try and figure out the equations of motion if initially, and let these be the equilibrium positions, we offset them by a certain amount. So that's going to be x1 for B1, that's going to be x2 for B2. And of course, it doesn't necessarily have to be to the right. If the value of x1 is negative, then it could very well be to the left. All right, so let's figure out how this is going to work. But this is really hard to approach directly. So what we're going to do, which I cover in my notes, is first we're going to take a hammer and nail B2 to the wall so that B2 is completely fixed and we can focus on B1. So in that scenario, it becomes simplified to something a little bit more like this. No, sorry. So we've got K and K prime right over here, and we've got B1 with mass M. And we're displacing it from its initial position by a certain amount x1. All right, so now we can just focus on exactly what these two springs do to B1 itself without considering the motion of B2 with it, because the motion of B2 itself also affects this. So what's the sum of the forces on B1? Well, let's say we displace it this way. So let's draw a mini diagram then. Unresponsive little. So then we've got something like this, where the spring with spring constant K is stretched out, and the spring with spring constant K prime is squeezed in. So what direction is the restoring force? Well, for this one, of course, it wants to go back to its original state in the middle, so it's going to approach the middle like that. And for this one, it also wants to go back to its original state in the middle, so it's also going to approach the middle like that, which means both of these forces will be in the exact opposite direction as x1, making the restoring force just, and actually what I'm going to do is I'm going to use thinner writing with this just to make everything look more consistent. So the total sum is going to be what? Well, it's going to be minus kx1, since that spring is going in the opposite direction, and minus k prime x1, since this other spring is also going in the opposite direction. But now we also have to separately consider the effects that B2's motion has on it. So we're going to nail B1 to the wall this time, and then consider how the force of B2 moving affects B1 without these other springs getting in the way. So you'll notice that this spring, if we move it this way, for example, in this direction, x2, then this spring is going to get dragged that way, making its restoring force travel this way, which is actually going to make B1 bounce in the opposite direction like this, meaning that it goes in the same exact direction as x2. So that means that to account for B2's motion, we have to add plus k x2. Oh, sorry, k prime x2. I was thinking of the wrong spring. So this is the final formula. And of course, if we want to find the same thing for B2, we just swap the numbers, since it's a symmetric case. But now, to get the solutions of this thing is a little bit complicated. We know by Newton's second law that the net force on an object is equal to the mass times the acceleration, or the mass times the second derivative of position. So let's consider that right here. This is equal to mx1 double dot, or the double derivative of x1 over time. So this is equal to minus kx1 minus k prime x1 plus k prime x2. And here we have mx double dot 2 is equal to minus kx2 minus k prime x2 plus k prime x1. But here's the problem. I mean, we have two separate functions in this equation. We don't know what x2 is, but yet we're using it to solve for x1. But here's the thing. Maybe we can solve for x2, but wait, that equation uses x1, which we were trying to solve for in the first place. So it seems circular, right? Well, there's actually a solution. This is a system of equations. So to solve it, we're going to have to add and subtract. So first, let's add these two equations together. What do we get? mx1 double dot plus mx2 double dot is equal to minus kx1 minus k prime x1. Oh, why did I do that? And then plus k prime x2. All right, and then we get the terms for mx2 double dot, which are minus k x2 minus k prime x2. Oh my gosh, I keep messing up again. Sorry. And plus k prime x 1. So then you'll notice some of our terms cancel out. Namely, these ones as well as these ones. So what do we get? Well, in total, we just get m times x1 double dot plus x2 double dot is equal to minus k times x1 plus x2. So now all we need to do is define a function y to be equal to x1 plus x2. Then this reduces to my double dot is equal to minus ky. So this is pretty simple to solve. All we need to do is plug in a trial solution. So since y prime prime is directly proportional, should have said y double dot, but I guess the old notation also works. Since y double dot is directly proportional to y, we can tell that this should be an exponential function, something like ae to the ct. And of course, we can also write this as ae I omega t, but this is a little bit more enlightening. So, of course, y prime is directly proportional to y, since it's just equal to c times ae to the ct, or cy. And y double prime is just equal to c squared y. So this should be pretty easy. And of course, I should write dot and double dot, but I'm getting a little bit mixed up. So we get c squared ae to the ct is equal to minus k over m times ae to the ct. So canceling these out, we get c squared equals minus k over m, or c is equal to I times the square root of k over m. So what does that mean? Well, our solution for x1 plus x2 is equal to e to the I rad k over mt. Oh, times the amplitude, of course, which is a times cosine of, oh crap, sorry, I'm kind of absent-minded today, rad k over mt. And you might ask, why are we disregarding the ai sine rad k over mt? Well, the reason is because for this to actually have a real effect, our time or our initial velocity would have to be imaginary, which means that since that's obviously not a very physical thing, we can just totally disregard this term. So this is what we get. But this is the sum of x1 plus x2. That doesn't really tell us anything about their individual motion. So we're also going to have to take the difference, x1 minus x2. So what does that give us? Now, in the notes, I take the difference of, let me just flip to that page real quick. So as you can see, in the notes, I take the difference x1 minus x2, but we can also do the opposite here, and I'll show you that that still works. So taking the difference mx double dot 2 minus mx double dot 1 is kx2 minus k prime x2 plus k prime x1. And then here, we just flip all the signs and add them. So plus kx1 plus k prime x1 minus k prime x2. And you can see none of the terms cancel, but some of the terms add, namely these terms and these terms. So we get m times x2 double dot minus x1 double dot is equal to minus k2 minus kx2 plus kx1 minus 2k prime x2 plus 2k prime x1. So it seems like we should write it as minus k plus 2k prime times x2. Let me see. Oh, crap. This would be minus k minus 2k prime times x2 plus k plus 2k prime times x1, which we can rewrite as k plus 2k prime times x2 minus x1. So we now define a function z to be equal to x2 minus x1, which means that z double dot is equal to k plus 2k prime times z. So what do we get? Well, we plug in the whole trial solution thing again. We get a e to the ct is equal to, wait a second. Oh, right. A e to the ct is equal to k plus 2k prime, and this would be c squared. I apologize. A e to the ct, which means that we get, cancel these two out, c squared is equal to k plus 2k prime. We get the g is equal to minus x2 plus x1, or x1 minus x2. Get the resultant minus m z dot dot is equal to k plus 2k prime times z. So, plugging in the trial solution like before, we get minus mc squared a e to the ct is equal to k plus 2k prime times a e to the ct. And as you can see, since we have mc squared, since e equals mc squared, get minus mc squared is equal to k plus 2k prime, meaning that we take c squared is equal to minus k plus 2k prime over m, or c is equal to the square root, well, I times the square root of k plus 2k prime over m. All right, so in the same fashion, well, first of all, we can see that this frequency is clearly very different from this frequency. So what I'm going to do is I'm going to term omega y as this frequency right over here, and omega z as this frequency right over here. And in the same way, I'm going to term ay as this, and I'm going to term az as well, what's going to come out of this. And we can also add a phase shift if we want, but I'm not going to do that right now. So that means that in the end, we have z equals x1 minus x2, and y equals x1 plus x2. But wait, that means we can obtain individual solutions for x1 and x2. Since x1 is just half of y plus z, and x2 is just equal to half of, well, let's figure it out. This is x2 plus x1. This is minus x2 minus x1. So it's just half of y minus z. So what does that get us? Well, we have half of what's y. Let's scroll down here. It's ay cosine the square root of k over mt plus az times cosine of the square root of k plus 2k prime over mt. And for the other one, we get half ay cosine rad k over mt minus a half, minus az cosine rad k plus 2k prime over mt. Alright, but we're not actually done, since we can actually find two very special cases for these. So let me look in my notes really quickly. Alright. So what we call normal modes are the two solutions we found for omega y and omega z. And we actually have two very special symmetric and anti-symmetric solutions. So the symmetric, let me look at the, so the symmetric oscillation mode is such that ay is equal to 1, or whatever other constant, az is equal to 0. But if az is equal to 0, as you can probably notice, then x1 is equal to x2, which is why we call it symmetric. And in fact, you can see that illustrated in this Desmos graph right over here. that I've included in the notes. And the anti-symmetric oscillation mode is quite similar, except that instead of AZ being 0, AY is equal to 0, which you might discover leads to x1 and x2 being negatives. So x1 is equal to minus x2, which you can see illustrated. I hate double-sided documents. Right over here. And we've also got a miscellaneous case where both AY and AZ are 1 in this image over here. So that's how you look at the equations for a coupled oscillator. And next time, we'll actually cover generalizing these oscillators with linear algebra.